Hello everyone, thanks for coming to this talk today. I'm Bazgen Tadevosan, I work at WorldQuant, and today we are going to discuss one paper from ICLR 2025 and its implementation. Before going into details, let's take a moment and understand what is modality. Modality is just a data type. For example, when you have image and text, those are two different modalities because they preserve information in different ways, even though the information might be quite the same. And we as humans perceive the world from multimodal signals. We simultaneously see, hear, touch, and feel, and those help us to make decisions in our environment. However, it was not the case with traditional machine learning, and traditionally, each models were trained one modality at a time. So you had only images working in computer vision or text when you were working in NLP. So there was this need to have a system which will learn generalized representation, which will capture this multimodality, right? And fortunately for us, with the emergence of self-supervised learning and their impressive capabilities, researchers could come up with a way to learn these representations after training on multimodal data. And later on, these representations can be easily used for various tasks, for downstream tasks after some fine-tuning. Let's take a look at two famous models, ICLR and CLIP. One uses intramodal, the other one cross-modal. But they share the same objective. The objective is contrastive learning. Let's take a closer look to CLIP. We have two modalities. One is a text and image. The idea is to learn embeddings in a way that you will end up in a scenario where those embeddings of two modalities, they become very close to another. You don't want that you will have an embedding of a text where dog is mentioned, but it's close to some other animal, right? So you want this similarity close when you have the same observation. But these models had one limitation. They learned only shared information. What I mean by this, so there is this terminology, partial information decomposition. So when you have label Y that you want to predict, and you have two different modalities, the information is consists of three different components. Redundancy, it is shared information. Sorry, the words might be confusing, but this is what they use in literature, so it's not really redundant. This is the shared information, uniqueness and synergy. So shared information is where you have image and text where cat is mentioned, right? This is shared information, but what if in an image you also have a dog, which is not mentioned in a text? So dog is also becoming unique information. And synergy, on the other hand, you get when you combine those modalities together. For example, sarcasm is a synergy. You can't detect sarcasm when you rely on only facial expression. You need more context to detect it. Right? So who is here familiar what is information or entropy? Cool. So information is a surprise that you get from a random variable, and entropy is average of that surprise. If I come up and ask you to predict the genre of the movie and just give you the title, so your entropy is high because there is high uncertainty. You can't predict the genre only based on the label. But once I show you the poster or plot, the entropy will decrease as uncertainty. And mutual information just asks this question: how much seeing one variable saves for you information for the one? How much knowing text? How much surprise will you get when you see the image? I'm sorry for these math equations, but if you look at it a couple of times, it will make sense. So just where we had these joint information, we apply chain rule, and we end up with this three equation. Here we can just see that when you have only one modality, when you have only one modality with the label, you only capture uniqueness and shared information. And with this three-way function, you can capture the synergy. But the key thing that I want to say here, clip only maximized shared information between those two modalities. We can go back and let's take a look here. So each had its own encoders, so they never attend one into another. So that's why they only learn shared information. We never fuse them. We maybe for fine tuning you can concatenate and fuse them, but in self-supervised settings they never attend one another, and you only learn this shared information. So you lose uniqueness and synergy there, and this is the problem that we are going to solve today. Oh, I need to go this way. Yeah. Okay, enough for the clip. Now let's talk about contrastive multimodal learning. So we have, again, each modality has its own encoders. It goes through latent converter. We concatenate them, fuse them in transformer block. In the end, you want to learn this representation, this embedding. We will see this Z many times here today, but the idea is to have this embedding in a way that it will capture synergy, uniqueness, and shared information. How to train such models where we are talking about unlabeled data? We still don't have the labels. And it turns out when you apply some augmentations, you can capture this information. Please treat X1 here as a representation where text is there, but you mask image. The same for X2, but the opposite image is there and you mask the text. And those X primes are just few views, but augmented. Correspondingly, this Z1 represents X1, but this time it's already embedding, and the rest corresponding the rest of the features. And once we have these embeddings, we can apply contrastive learning, right? I try to avoid to dive into math a lot, but I want to build some intuition. I think it's not very hard to understand. So the idea is that they have this assumption. When you have label and you have all features together, here X is both modalities, all modalities together. It says that there exists some augmentation strategy that can capture all information as if you had the label as well. So you don't need to have label. When you have multimodal data, you can approximate that information. Once you have this, you can approximate this Z prime, and you can capture all components that we've discussed alongside with the synergy. And explicitly, we can also use one modality where the other one is masked. We can capture shared information and uniqueness. Let's just recall what is influency. It's just standard loss which is applied in contrastive learning. You just want to maximize the ratio, because in numerator you have positive pairs, denominator negative pairs, and you can just put minus in front. It will become loss for you to minimize. And CoMM is basically applying this influency few times with the features that we've discussed. So in first component, we have full views against one another, and in the other component of the loss, we can capture shared information and uniqueness. Just for you to remember, we have those, right? So Z1 is a representation of one modality where the other one masked, and primes are when they are concatenated and some augmentation strategy was applied. Okay, now let's talk about the implementation. So the problem that we are going to apply our solution is multi-label genre prediction. Here you need to capture those pieces of information to be able to classify movie, and we are dealing with multi-label classification, so each movie can be up to, I don't know, many labels, but here in this example we have 23 labels. The data set that I used is the same that the authors, one of the data set that the authors of the paper used. We have 25 movies paired with plot and fantasy. The sample here, you see a very good movie, Seventh Seal. If you are into chess or philosophy, I recommend you to watch this movie. It's about one guy who came from the war and he was unhappy. Dad came to take his life away, and he somehow convinced Dad to play chess to prolong his days. The dialogue is there very good, and my professor used to say that ultimate goal of AI is to prefer this over Kardashians. Yeah, so enough. We still, as I said, had our encoders. We need to freeze those encoders. I use for text Q format from Blip tool, and for images VITG. Those things are going to be freezed for us while training. Yeah, I just want to, you don't have to understand all the code, but just want to show that the implementation is much easier than the concepts. So we just have one transformer block with CLS learnable token, which we prepend after this concatenation, just with 8 heads. For image augmentation, the whole configuration was taken from ICLR paper, the same grayscale. I randomly flipped the images, basically the same. For text, I just randomly mask 15% of the tokens. That's it. And we, now about the loss, fortunately for us, InfoNC is implemented by PyTorch, and I just for CoMM constructed with just basic algebra. And that's it. We have everything what we need for pre-training. And I use some hyperparameters. Basically, I use warm-up cosine scheduler. I turn 100 epochs. Okay, once pre-training is done, and we need to classify this label, right? So we can freeze the whole architecture. And the beauty about this, that these representations can be applied in many different tasks. So you are not limited to one specific task. And actually, fine-tuning is much, much easier. You just need to have one single liner probe. 23 is the number of labels. There is multi-label classification. We use our familiar binary cross-entropy. And the rest is quite similar. And we can see whether this setup is working or not. Some plots, we see that the losses converge in pre-training. For fine-tuning, we achieve weighted F1 score 0.62 and macro F1 score 0.53, which is quite good when you are dealing with multi-label classifications and number of labels are 23. And we can see it outperforms all the other benchmark models. And this is just a one simple example out of few experiments they have done. They've also generated synthetic data where they explicitly had synergy generated with some XOR function. So even in that setup, they outperform the rest of the models. The takeaway is that when you are dealing with multimodal learning, you need to be aware of those pieces of components that you need to capture. The budget is quite small. We saw that it's just basic transformer block, and yep. I guess that's pretty much it. I hope you learned something new today, and happy to take any questions if you have some.
Presentation. Are there any questions?
Thank you for the talk. For the classification, do you use all of the embeddings combined, like the shared ones, the redundant ones? And also a second question, Is there a way to verify that indeed the redundant ones learn the same information and the not shared ones learn different information and are also helpful?
Yeah. Great question. Let's go back. So the architecture we saw, this one, right? After the training, you just concatenate them, and with this contrastive objective, while training, you had these 4 Zs, right? When you compare that, but in inference time, you just concatenate them and fuse them, and you already have this embedding. So no need already to do masking or augmenting. It will generate for you the first one. For the second question, they had this synthetic dataset, which is called tree feature. They explicitly have shared information, uniqueness, and synergy with XOR function. Even in that setup, they show that CoMM performs much better than the benchmark. So they actually prove it there. Thank you.
Okay, nice. Any other questions? Okay. I'll ask one. As I have a chance, exclusive chance. As I'm totally newbie to this subject, how long does training take? How long is the feedback loop for you as designer, developer of this thing to be able to detect, or, oh, something went wrong, I'm going to do it again?
Yeah. So I'm not the author of the paper. So I know one of the authors, Benoit. I used to work with him on another research, but that research is closed because he's in industry, myself as well. So about implementing for this, it was 2 years ago. It took a month for me to get familiar with the topic, with multimodal learning. I think even more, because it required also to recall voice information theory for the training. The dataset that I used was 25,000 observations, and I think just few hours on A100. I use A100 GPU for pre-training. That amount of time, few hours, so not big when you are because the dataset is small, and that's the benefit. So the budget is small, and you can compare with models such as Clip, which was trained on a tremendous amount of data.
Okay, thank you.
Thank you.
Yes.
So thank you for the presentation. And the question that I would like to ask is that you have mentioned that you have 23 genres, if I'm not mistaken, but there are some genres that are part of the broader genre. How are you going to get information from the embeddings, for example, to detect a genre that is not so popular?
Yeah. So, good question. We are talking here about imbalanced data, where you have some labels which are not enough to represent the whole observation, right? So when you have imbalanced data, like few examples, you can synthetically generate similar movies, even if those are not real movies. So you can generate some text and some plot just to mimic those and try to learn them. So this is one strategy. Another one will be, if you have enough dataset, undersampling. So if drama is majority of the classes, you can just randomly remove some dramas and makes this fairness there.
What about grouping them in a broad genre and after that do prediction?
That's a good, that's a good way to do some research and see what genres ended up together. Yeah, but that's good direction. Yeah, it needs to be explored.